In this lesson, we will derive the differential form of the conservation of linear momentum equations for a control volume, which are commonly called the Navier-Stokes equations. Here we have a small fluid element of dimensions dx, dy, dz, and a mass dm. The fluid element is subjected to various external forces, df1, df2, and df3. These forces may act at the surface or on the entire mass. Since these forces are acting on a small mass dm, we place a lowercase d in front of the forces to indicate that they are small as well. Currently, we are observing the fluid element as it moves through space, which means we are adopting a Lagrangian point of view. Applying Newton's second law for this fluid element in a Lagrangian point of view gives us the sum of external forces on the fluid element, dF external, equals the mass dm times the acceleration of the fluid element a. The acceleration is the time rate of change of the velocity v, and we will use a capital D in dv dt to indicate that we are referring to the total derivative. Since this equation is Lagrangian in nature, it tells us how this particular fluid element's motion will respond to forces. If we want to know the entire flow field, that is, how the entire flow behaves at each point in space, we must convert this equation into an Eulerian description. Since we are using Newton's second law from the Lagrangian point of view, we will temporarily use the subscript Lag to remind ourselves which terms are Lagrangian in nature. We now create a control volume using red dashed lines that exactly surrounds the mass. And recall that if we observe a region of space, such as the control volume shown here, we are using an Eulerian point of view. At this particular moment in time, someone observing the mass dm using a Lagrangian point of view would observe the exact same mass as someone observing the control volume, which is the Eulerian point of view. So the mass dm from the Lagrangian point of view is equal to the mass dm from the Eulerian point of view, where here we use the subscript EUL to refer to a quantity in the Eulerian point of view. Similarly, the external forces acting on the mass dm are the same forces acting on the mass inside the control volume. So the sum of external forces from the Lagrangian point of view is equal to the sum of external forces from the Eulerian point of view. We plug in the two Eulerian terms into Newton's second law, and the only term that is still Lagrangian is the acceleration dv dt. The time rate of change of a variable in the Lagrangian point of view can be related to the time rate of change of the variable in the Eulerian point of view using the material derivative. In a prior video, we derived the material derivative for a generic variable alpha, where alpha could be a scalar field or a vector field. And in our case, the variable of interest is the velocity v. The material derivative states that the total derivative, dv dt, is equal to partial v partial t plus the velocity vector dot the del operator, which operates on the velocity vector. The left side of the equation represents the Lagrangian point of view, and the right side of the equation represents the Eulerian point of view. After plugging the Eulerian expression into Newton's second law, we have dm times the quantity partial v partial t plus v dot del operator v equals the sum of external forces. Since all three terms are now in the Eulerian point of view, we will drop the EUL subscript, and the resulting equation applies to all points in space. We now need to discuss what types of external forces act on the fluid in the control volume. The external forces can be separated into body forces and surface forces. Body forces act on the entire mass inside the control volume. In most systems, the main body force of interest is the gravitational force, which is mass dm times the gravitational acceleration g. Since g is a vector, we can separate it into its components, which in a rectangular coordinate system would give gx I hat plus gy j hat plus gz k hat. The surface forces act only at the surface of the control volume, and we can break them up into three components as well. Here we have a surface force acting on a small area dA. We can decompose the force vector into a component that is normal to the surface and two components that are tangent to the surface. If we are using a rectangular coordinate system, the surface force vector becomes the sum of the surface force components in the x direction, I hat, plus the sum of the surface force components in the y direction, j hat, plus the sum of the surface force components in the z direction, k hat. It is more convenient to express the surface forces in terms of the stresses which act at the surfaces. Stresses can be thought of as the intensity of a force and has units of force per area. We will analyze the stresses acting on a small cube-shaped control volume of dimensions dx, dy, and dz. The center of the control volume is at a point x, y, z. For now, we will use the symbol sigma for all the stresses. Since stresses can act on different surfaces of a fluid element and act in different directions on a given surface, we will need two indices, which we will put as subscripts to describe each stress. The first subscript I refers to the surface on which the stress acts, as indicated by the normal vectors n hat. For example, a stress that acts on the right or left side will have y for the subscript since the normal vector points in the y direction. The second subscript j refers to the direction of the stress. For example, the stress on the right surface that acts in the y direction is denoted as sigma yy. Notice that the arrow representing sigma yy on the right surface was drawn pointing in the positive y direction. This is due to the convention that we will adopt for indicating the positive direction of each stress. If the surface's normal vector, n hat, points in the positive direction of coordinate I, the stress is considered positive in the positive direction of the coordinate j. So the stress on the right surface that acts in the z direction, which is denoted as sigma yz, is considered positive in the positive z direction. And the stress on the right surface that acts in the x direction, which is denoted as sigma yx, is considered positive in the positive x direction. For surfaces with normal vectors that point in the negative direction of the coordinate I, the stress is positive in the negative direction of coordinate j. For example, notice that the normal vector on the left side points in the negative direction of y. This means sigma yy on the left surface points in the negative direction of y. Sigma yz on the left surface points in the negative direction of z, and sigma yx on the left surface points in the negative direction of x. The stresses on the left side are drawn with dashed lines to indicate they normally would not be seen from the current vantage point. We're also using a color scheme for the arrows. The stresses that act in the y direction are indicated by red arrows, the stresses that act in the x direction are indicated by blue arrows, and the stresses which act in the z direction are indicated by purple arrows. At the top surface, which points in the positive direction of z, the first subscript of the three stresses is z. Sigma zz points in the positive direction of z, sigma zx points in the positive direction of x, and sigma zy points in the positive direction of y. We could continue to draw the stresses that act on the bottom surface, front surface, and rear surface, but the image would become a bit too cluttered. So instead, let's focus only on the stresses that act in the y direction. There are still three stresses that we need to draw. On the bottom surface, which is oriented in the negative direction of z, sigma zy points in the negative direction of y. On the front surface, which is oriented in the positive direction of x, sigma xy points in the positive direction of y. And finally, on the rear surface, which is oriented in the negative direction of x, sigma xy points in the negative direction of y. Now we will derive an expression for the resultant force produced by the stresses in the y direction. First, we examine the force produced by stress sigma yy. Notice sigma yy on the right surface acts at a distance 1/2 dy from the center of the control volume. We will denote this stress as sigma yy at location y plus dy over 2. Sigma yy on the left surface acts at a distance negative 1/2 dy from the center of the control volume. We will denote this stress as sigma yy at location y minus dy over 2. We can relate the stress at the side of a control volume to the center of the control volume using a Taylor series approximation where we keep just the first two terms of the Taylor series. Sigma yy at the right surface is approximately sigma yy at the center plus the first derivative of sigma yy with respect to y times the distance between the right surface and center, dy over 2. We've dropped all terms that have a dy squared or higher from the Taylor series because they are very small for a very small control volume. Since dy is a very short distance, dy squared is much smaller, dy cubed is even smaller, and so on. Similarly, sigma yy at the left surface is approximately sigma yy at the center minus the first derivative of sigma yy with respect to y times the distance between the left surface and center, which is dy over 2. In order to find the resultant force due to the stresses sigma yy, we multiply the stresses by the area on which the stresses act. The area on the left and right surfaces is dx times dz. So we multiply sigma yy by dx dz to get the forces caused by sigma yy. The resultant force due to the stress sigma yy is sigma yy at the right surface times dx dz minus sigma yy at the left surface times dx dz. The minus sign appears because sigma yy on the left side points in the negative y direction. We plug in the approximations for sigma yy at the right and left surfaces, and notice that the sigma yy terms cancel out. This leaves us with partial sigma yy partial y times dy dx dz, and dy dx dz is the volume of the fluid element dv. So the resultant force due to the sigma yy stresses is partial sigma yy partial y times the volume. Now we turn our attention to the resultant force caused by the sigma zy stresses. Sigma zy acts at the top surface at a distance 1/2 dz from the center of the control volume. We will denote this as sigma zy at location z plus dz over 2. Sigma zy on the bottom surface acts at a distance negative dz over 2 from the center of the control volume. And we will denote this as sigma zy at location z minus dz over 2. We use a Taylor series approximation to relate the stresses at the top and bottom surfaces to the center of the control volume. Sigma zy at the top surface is approximately sigma zy at the center plus partial sigma zy partial z times the distance between the top surface and center, dz over 2. We neglect all terms that are dz squared and higher because they are very small for a small control volume. Similarly, sigma zy at the bottom surface is approximately sigma zy at the center minus partial sigma zy partial z times the distance between the bottom surface and center, dz over 2. In order to find the resultant force due to the stresses sigma zy, we multiply the stresses by the area on which the stresses act. So we multiply sigma zy by dx dy to get the forces caused by sigma zy. The resultant force due to sigma zy is sigma zy at the top surface times dx dy minus sigma zy at the bottom surface times dx dy. And the minus sign appears because sigma zy on the bottom surface points in the negative y direction. We plug in the expressions for sigma zy at the top and bottom surfaces, and the sigma zy terms cancel out. This leaves us with partial sigma zy partial z times dz dx dy. And dz dx dy is simply the volume dv. So the resultant force due to the sigma zy stresses is partial sigma zy partial z times the volume. Finally, we determine the resultant force caused by the sigma xy stresses. Sigma xy acts at the front surface at a distance dx over 2 from the center of the control volume, and we will denote this as sigma xy at location x plus dx over 2. Sigma xy on the rear surface acts at a distance negative dx over 2 from the center of the control volume, and we will denote this as sigma xy at location x minus dx over 2. We once again can use a Taylor series approximation to relate the stresses at the front and rear surfaces to the center of the control volume. Sigma xy at the front surface is approximately sigma xy at the center plus partial sigma xy partial x times the distance between the front surface and center, which is dx over 2. We neglect all terms that are dx squared and higher because they are very small for a small control volume. Sigma xy at the rear surface is approximately sigma xy at the center minus partial sigma xy partial x times the distance between the rear surface and center, dx over 2. In order to find the forces due to the stresses, we multiply the stresses by the area on which the stresses act. And the area of the front and rear surfaces is dy times dz. So we multiply sigma xy by dy dz to obtain the forces caused by sigma xy. The resultant force due to sigma xy is sigma xy at the front surface times dy dz minus sigma xy at the rear surface times dy dz. The minus sign appears because sigma xy on the rear surface points in the negative y direction. We plug in the expressions for sigma xy at the front and rear surfaces, and the sigma xy terms cancel out. This leaves us with partial sigma xy partial x times dx dy dz, and dx dy dz is simply dv. So the resultant force due to the sigma xy stresses is partial sigma xy partial x times the volume. The sum of all surface forces in the y direction is partial sigma xy partial x plus partial sigma yy partial y plus partial sigma zy partial z times the volume dv. If we repeat this process to find the surface forces in the x direction and z direction, the sum of all surface forces in the x direction is partial sigma xx partial x plus partial sigma yx partial y plus partial sigma zx partial z times the volume dv. We've already found the sum of all surface forces in the y direction, and we would find that the sum of all surface forces in the z direction is partial sigma xz partial x plus partial sigma yz partial y plus partial sigma zz partial z times the volume dv. Notice that we've added the unit vectors I hat, j hat, k hat to indicate the direction of each force component. Let's return to Newton's second law. In the left side of the equation, the velocity vector appears a few times. And recall that the velocity vector has a component in the x direction, u, a component in the y direction, v, and a component in the z direction, w. We plug in the expression for the velocity into the v dot del term and apply the dot product to obtain u partial velocity partial x plus v partial velocity partial y plus w partial velocity partial z. On the right side of the equation, we plug in the expression for the body forces and the expression for the surface forces. We now plug in the expression for the velocity vector into all terms on the left side and then collect the terms that have the same unit vector. The left side of the equation becomes mass dm times the quantity partial u partial t plus u partial x plus v partial u partial y plus w partial u partial z I hat plus mass dm times the quantity partial v partial t plus u partial v partial x plus v partial y plus w partial v partial z j hat plus mass dm times the quantity partial w partial t plus u partial w partial x plus v partial w partial y plus w partial z k hat. Next, we equate the components in the x direction, y direction, and z direction and divide by the volume dv. The terms that have an I hat on the left side of the equation are set equal to the terms that have an I hat on the right side of the equation. The terms that have a j hat on the left side of the equation are set equal to the terms that have a j hat on the right side of the equation. And the terms that have a k hat on the left side of the equation are set equal to the terms that have a k hat on the right side of the equation. The density rho appears since we divided the mass dm by the volume dv. Now we will focus on better defining the stresses. At this point in the derivation, it should be noted that the discussion of stresses will be simplified somewhat to be appropriate for an undergraduate fluid mechanics course. This will allow us to avoid more advanced mathematical concepts such as fourth-order tensors. Graduate-level fluid mechanics textbooks will define the stresses in a more thorough manner. Now, the stresses can cause the fluid to deform. In a prior video, we discussed how fluid elements can experience linear strain and shear strain based on velocity gradients in the flow. We will denote the stresses that cause linear strain and shear strain as tau ij. These are often called viscous stresses because, as we'll see, they are related to the fluid viscosity and the deformation of the fluid. The normal stresses, where the two subscripts are the same, are a combination of pressure and viscous stresses and can be rewritten in the following manner. Sigma xx is equal to negative pressure plus viscous stress tau xx. Sigma yy is equal to negative pressure plus viscous stress tau yy. And sigma zz is equal to negative pressure plus viscous stress tau zz. The pressure has a negative sign because it always points inward in the opposite direction of the normal vector n hat. Tau xx, tau yy, and tau zz represent the viscous stress caused by a fluid element stretching in the direction of the velocity gradients. The 6 remaining stresses, where the two subscripts are different, represent shear stresses and cause fluid elements to undergo shear strain. We replace sigma xy with viscous stress tau xy. Sigma xz is replaced with viscous stress tau xz. Sigma yx is replaced with viscous stress tau yx. Sigma yz is replaced by viscous stress tau yz. Sigma zx is replaced with viscous stress tau zx. And sigma zy is replaced with viscous stress tau zy. We plug in the new expressions for the stresses into the equations and separate out the terms that have pressure. Our equations have come a long way from the original form of Newton's second law at the beginning of this video. Now let's take a moment to review the meaning of each of the terms. The left side of the equation is mass per volume times acceleration. The forces causing the acceleration are on the right side of the equation. The terms with density times gravitational acceleration represent the gravitational force per volume. The terms with partial derivatives of pressure represent the pressure force per volume. And the terms with the viscous stresses represent the viscous forces per volume. At this point, we have 14 unknowns, but only 3 equations. The unknowns are the 3 velocity components, u, v, w, the density rho, pressure p, and 9 viscous stresses. If we include the conservation of mass equation, we have a 4th equation. Although not shown in this video, it can be proven that shear stresses on a small fluid element are symmetric. That is, tau xy is equal to tau yx, tau xz is equal to tau zx, and tau yz is equal to tau zy. Now we have 11 variables, but still only 4 equations. The 3 conservation of momentum equations and the continuity equation. These 4 equations apply at every point in space, and if we could solve the equations for u, v, and w, we would know the entire flow field. But at this point in the derivation, we are stuck unless we make some assumptions about the flow which will allow us to reduce the number of unknowns. This will be the subject of the next video.